So Tom, when he was organizing this 65th anniversary series, he asked me to talk about airborne science, and I greatly appreciated the invitation. He actually came up with the first draft title of the talk, and I couldn't come up with anything better. I kind of liked it. I don't know if I had the same intention as Tom did. I think most of you, certainly those of you who are from here, from LASP, understand that LASP excels in observations from space, including observations of the Earth. So when I think of extending observations of the Earth from above, I mean extending them from high in Earth orbit down to much lower in the atmosphere. So that's my interpretation of this. And this is something I think is pretty new for LASP, although as I think you'll see, I hope I convince you that LASP is actually beginning to be very, very active in airborne science, and I think that we have a strong future in this. Here's my outline. Why do we do airborne science? What is the role of airborne science in our science observations? And it's not obvious. It's not necessarily obvious, especially when you think of some of the problems that we study. I'm going to spend time on history, maybe a lot of time on history. This was the fun part. You know, there's an abundance of material that I could draw from, and when I started to think about my own history, this actually became a little, or quite a lot of fun for me. So I'm going to spend some time on the history, a little bit on the history of the airborne sciences. By no means thorough. In fact, it's not thorough at all. I give maybe one example of maybe the biggest achievement in airborne science, and then some of my own personal history and how I got started down this path. When I call some pretty cool platforms, this is interspersed throughout the talk, but part of the fun in doing this is some of the exotic aircraft that we fly instruments on. And then I come to recent times and some recent missions that were either led by LASP or had very strong LASP components, including some of them, and include my own group's research. And then some future missions and what role LASP has as we look ahead to the next decade. Finally, we have a few undergraduates in the audience. I'm going to talk about some great student opportunities. This talk is NASA-centric. Probably nobody reads the abstract. I certainly don't read abstracts before I go to a talk. I read the title. But in the abstract, I talked about Department of Energy, NSF, NRL, all sorts of other funding agency flight programs. And they all have flight programs, and many of them I've participated in. But, you know, after looking back on this, you know, NASA really is the leader. My origin is NASA, and a lot of the people that you'll see involved here are from NASA. So it's pretty easy to make this a NASA-centric. It's not exclusively NASA. So a little bit of orientation first about the structure of the atmosphere, where we are in the atmosphere, or well, we know where we are in the atmosphere, but what portion of the atmosphere where we make these measurements. And so this red curve here is a temperature profile. You'll see the temperature here. Doesn't really matter what the value of the temperature is. Other than the important thing here is to note that in the troposphere, this lowest 10 kilometers of the atmosphere, temperature decreases. Okay, up to about 10 kilometers where it doesn't decrease anymore, stays constant, and then starts to increase. Increases in the stratosphere. The cause of the increase is due to heating by ozone. Then by about 50 kilometers, it becomes steady again, then decreases again in the mesosphere, reaches the mesopause region, and increases again in the thermosphere, and then you get this slow blending into space beyond there, the exosphere. Commercial aircraft fly at about 10 kilometers. A lot of the research aircraft that we've flown instruments on fly at 10 kilometers or below. This, I guess, is meant, I didn't draw this, by the way. This is meant, I think, to depict an unpressurized aircraft, about the highest that a pilot could fly without the aid of oxygen. I've been on unpressurized aircraft flying as high as 20,000 feet, and it's mandatory that you start taking oxygen at 16,000. You usually need it before then. One of the aircraft that I'm going to highlight, it's not shown here. Well, here it shows a supersonic plane, but here I'm going to talk about a subsonic plane called the NASA ER-2. Probably some of you are aware of that. That flies about here. That's about the limit for research aircraft. Beyond there, this depicts a radiosonde, which is a launch from the surface of a package that measures variables for weather. We also have other research balloons that go up to about 30,000 feet, a little bit beyond, or 30 kilometers, 100,000, 110 to 120,000 feet. Beyond there, that's the subject of talks you've heard in other portions of this series, I hope. Tom Woods did sounding rockets. We had a lot on our space assets. So I'm down here in these aircraft, some with people in them, some without people in them. I wonder what this poor guy has in store for him. Dropping right into the thunderstorm. But what kind of measurements do we make? I'm not going to spend a lot of time on the actual measurements. Most of the talk is geared toward the bigger picture things. But when we make Earth observations, we measure things like aircraft state and thermodynamic variables, pressure, temperature, humidity, wind speed, things like that. We also measure gases from aircraft, trace gases especially, not the boring things like nitrogen and oxygen, but things like ozone, water vapor, nitrous oxide, all sorts of things that can be very, very important for studying the atmosphere. We measure aerosol particles, little particles of condensed matter which can reflect sunlight, they can absorb radiation, they can serve as sites for water to condense and form cloud droplets. We also measure cloud droplets and precipitation-sized droplets. But these topics here, atmospheric radiation, hyperspectral remote sensing, these are really the core of my own research, and much of the science that I'll focus on here comes from these topics. And this cartoon sort of explains why. What this is, ignoring the numbers for a moment, or the left side here depicts solar radiation. All of the energy that comes from the sun at the top of the atmosphere transmits through the atmosphere, interacts with clouds, interacts with the cloud-free atmosphere, which is both gases and these things that we call aerosol particles. And some of that is transmitted to the surface and some is reflected to the space. The right-hand part of the diagram depicts the infrared radiation that's emitted by the surface, emitted by the clouds, emitted by the greenhouse gases in the atmosphere. And all of these things, the energy is exchanged and transmitted throughout this whole system. Eventually there has to be balance over space and time. Well, there doesn't have to be balance though, and there's balance if temperature doesn't change, or for temperature not to change, there has to be balance. Energy in has to equal energy out. We think that we're living in a rather remarkable time where climate is changing, and we think it's changing pretty rapidly. And we can estimate that there are imbalances in this global energy picture. And so this is really the heart of why we make measurements of radiation in the atmosphere, outside of the atmosphere, putting this whole picture together. So back to this question of why do we make airborne measurements though? I mean, you saw that picture. All of those numbers on there, those represented averages over time and over space. And the space is the entire globe. What could you possibly do on an aircraft? The campaigns last on the order of months, maybe 2 months. You're certainly not flying an aircraft that entire time. You have a few hours per day. You have snapshots in space and time. We need this global picture that we get from satellites and ground networks. And so what role can aircraft play in understanding this big picture? This is all lifted from the NASA Airborne Science program, maybe an abridged version of things that you'll find on this webpage. And actually quite good webpage, especially by NASA standards. I was a former employee, so I'm allowed to joke, right? So what do we do with airborne measurements? Well, we can calibrate instruments in space, okay? We can underfly instruments in space and make calibrations. We can also make measurements of the exact properties that we're trying to infer remotely from space. So that's very important. We can validate these remote retrievals that we do from space. We can develop new sensors. We can test instruments. You know, it's a very risky proposition to build a new instrument and launch it into space, because you're not going to get that instrument back again. It has to work perfectly. It often has to be self-calibrated. It's a tremendous effort, and aircraft provide us platforms, and balloons, by the way. I apologize, I keep saying aircraft, but balloons are included in this talk as well. These offer platforms to test and advance the technologies that we're eventually going to fly into space. Here's a really big one, though: process studies. We can measure. You know, when I said that we measure snapshots in space and time, those snapshots are actually extremely important. We can get into the details and the heart of things and look at it on spatial and time scales that you simply can't do from space. So this is very, very important. And then we blend this with the larger view from space, and develop a larger picture of the Earth system. This is not a trivial one here at all. Develop the next generation of scientists and engineers. We employ a lot of students in this program. This is a great test bed, or a great program for training students, and I'm going to talk about this at the end of the talk. So, wait. Sorry, I have to play a video here. If I can see there it is. This is actually a YouTube video. You can search for it. I got this directly from Rick Shetter, who runs the NASA DC-8 at the University of North Dakota. It's contracted out through North Dakota. This shows a lot of the aircraft that NASA flies, many of which that we flew on. The first was the Global Hawk we flew on, the DC-8, ER-2. Sherpa's a new plane in the NASA fold. We haven't flown on that yet. All sorts of different missions here. I hope you enjoy the music. I decided to keep the volume on for you. Here's a camera from the Global Hawk. The Global Hawk is an unmanned vehicle. There's something on the window that I'm trying to figure out what it is of this camera. Global Hawk coming in for a landing. It's the hangar down at Edwards. Bruce Kendall spent a lot of time there. Those are pilots flying a plane with that mouse right there. This is the Operations Center. Scientists can monitor their aircraft. It's telemetered in real time. Not so simple to actually get that in the air, though. Would you say, Bruce? There's a workhorse right there, P3. NOAA has several P3s. This is a great view here, flying up this Greenland Glacier. NASA's doing what's called an Ice Bridge mission, which is a continuity cryosphere mission, continuity before until Cryosat 2 launches. Gives us information. What's that? ISAT. Yeah, what the next one? Cryosat, yeah. I just named the mission. ISAT 2. DC-8. They pause this so that you can see this crack in the ice. And then they do modeling. This is fascinating here. Digital mapping system imagery on the right of the imagery, the real imagery on the left.
How wide is that?
Oh, good question. I think, what was that movie? Didn't somebody fall in that movie, Day After Tomorrow? It actually opened up, I think, during the movie. He jumped over it, I think. We were laughing like that. And, oh, there it is, Student Airborne Research Program. This is a great program. You don't know this mission, rapid intensification. Yeah, this is a pretty cool flight here. I don't know which Earl. Do you know what year Earl is? They're inside the wall right now. And now you're seeing the forward wall. Look at that. And now they're just entering it, and you can see but that's the least turbulent level of the entire vertical. This is a nice thing here. Empty DC-8. They're instrumented. They're putting in all the instrument racks, instruments themselves. Even the seats will come in later. And there's first-class seating on the DC-8. Spent many a 10 to 12-hour flight on the DC-8. A mission that our instruments flew in 2 years ago, in 2012. Look at this. How would you like to be this guy? Flying in that contrail. That can't be. Synthetic aperture radar imaging. That's the G3. And there is the queen of them all, the ER2. Dragon Lady, did you know it was called Dragon Lady? Maybe we saw some moss in this. I don't know what Sherpa's used for. One of the newer. It's remarkable how many aircraft that NASA has in this program. I mean, remarkable even for somebody who's been a part of this program for 25 years now. Okay. So, I thought I should start, in terms of science, well, almost really start and end with perhaps, well, not perhaps, I mean, I think it certainly is recognized as the biggest achievement in the airborne science program, and it's one of the biggest achievements in all of Earth science, of Earth atmosphere science, and that is the 1987 flights of the ER2, which provided an unambiguous link between ozone loss and human-emitted chlorofluorocarbons. Chlorofluorocarbons are the things that used to be used as propellants in spray cans. They were also used as refrigerants in compressors, air conditioning, refrigeration. And I thought I'd better do a little bit of ozone science here first as a background to make sure you know what you're looking at here. These are images of the southern hemisphere from the total ozone mapping spectrometer called TOMS. With this big target you see in the bottom here is the South Pole. This is called the Southern Polar Vortex. And this purple and blue region is where you have very low ozone amounts. These numbers here are in what we call Dobson units. A Dobson unit is simply if you compress the ozone in the column to standard pressure, surface pressure, and standard temperature. The one Dobson unit is 1/100th of a millimeter. So if 300 Dobson units are a sort of typical ozone amount, you'd have 3 millimeters of ozone. Not much, but extremely important. And so you see it here. You've heard of the ozone hole. Ozone hole does not mean no ozone at all. We define a hole when the thickness in terms of Dobson units is below 225. Why that threshold? Below that threshold, we lose a lot of the protective veiling that we get from ozone. It's insufficient to prevent harmful ultraviolet radiation from reaching the surface. We'd been measuring ozone at the Halley Bay site in Antarctica as early as the 1950s, launching ozone sondes, and you could see up till about 1980 there was evidence of a small decrease. A lot of the science in understanding ozone chemistry was developed in the 1970s, and the people that eventually won the Nobel Prize for this did the bulk of their work actually in the mid-70s. Before that, we see this thing sort of fall off the cliff in the 1980s and really plummeted. Now we come to the satellite era, TOMS, and we see agreement between satellite and the surface observations, and things get very, very low here. So you'd say from here on, this is a hole. So this famous experiment, 1987, one of the earliest airborne experiments done at NASA Ames with the ER2. NASA had been using these to do surface imagery long before this, but for doing atmospheric science, this really started in the 1980s, this platform. This was perhaps the second really large mission for the ER2. Some of these instruments that measured chlorine and bromine were developed specifically for this experiment, but this is a smoking gun here showing chlorine monoxide, and this is latitude degrees south. As you get further south into the so-called polar vortex, where everything's pretty wrapped up, there's very little exchange from within the vortex without. So you can really do chemistry there, because something gets in there, it's not going to get back out of the vortex. And so you see this large increase in chlorine inside the vortex and this big fall off of ozone from within. And we have several in the audience, including Eric Richard, who know the history of this far better than I do. But one could argue that without something like this, the guys who came up with the chemistry in the 70s would have never won their Nobel Prize. This was really the evidence. So this is some information more on how chlorine destroys ozone. In the interest of time, I won't get in. I won't say much about this, other than a single chlorine atom can remove as many as 100,000 ozone molecules. So it's very, very effective at removing ozone. The vortex is important, but also what happens in Antarctica is you have what are called polar stratospheric clouds. You have ice particles that promote this ozone chemistry on the surface, and so that's an important thing also in the whole process. So that's a major accomplishment. Unfortunately, I hadn't arrived at Ames yet, and so I did not take part in that, but I think that was probably the start of many other achievements. I just wanted to bring that up because that was the only Nobel Prize that was ever awarded in atmospheric sciences came from the ozone hole and understanding the chemistry involved in it. It was 1995 award, I believe. So I said that I'd intersperse this with talks about the platforms, and the ER2 is really a remarkable platform. It flies very high, 70,000 feet. It has a pretty long duration. It can go as long as 10 hours, depending upon the payload. But it traces its heritage to this, the famous U-2 aircraft. And I can look in my audience and know that many here know the significance of the U-2. And I'll say a little bit about it here. So this is a modified version of the U-2 spy plane. This plane was developed to do reconnaissance over the former Soviet Union. It was developed, it was to fly at 70,000 feet, which in the 1950s, it was considered that this was beyond the reach of Soviet fighters, missiles, and radar. We learned a little bit later that, well, not quite. There are significant differences. Well, first of all, so a little bit about that history. In 1960 in May of 1960 was a time where a U-2 was being tracked on Soviet radar. It's interesting, the history you read about it, they actually were doing the flights on May Day, which is probably not a wise thing to do in a communist country because it was shut down for holiday. There were no other flights, and so it's pretty easy to see things, that shouldn't be there, shouldn't be flying. So it was being tracked. They launched a missile which detonated behind the U-2. It was enough to disrupt the flight, and Gary Powers had to eject. He survived. A lot of the planes survived. The Soviets learned a lot about the U-2 at that time. But NASA, the CIA or the Air Force, or a combination of the two, decided, well, what do we do? And they said, well, there's no way that the pilot survived. They didn't think a pilot could survive ejecting at 70,000 feet. They figured that Powers was dead. Let's tell them it was a NASA plane. NASA was apparently flying their own U-2 over Turkey at the time, and the story was that this strayed into Soviet airspace. The pilot was incapacitated, and that was the story. Khrushchev let them go along with that story for several days, actually, until he was amused enough that he finally said, hey, we have your pilot here, and he's already told us what he's doing. So it was a big embarrassment. Dulles, who was the head of the CIA at the time, offered to resign. Probably later, Eisenhower wished he accepted it, but it didn't at the time. Powers was exchanged, I don't know, was it years or months later? He was held prisoner for a while. There was a prisoner exchange. And so one of the more embarrassing moments in our history in the Cold War. But nevertheless, a remarkable platform. It's been a remarkable platform for science. There are differences, longer wingspan than the U-2. It's got a lot of other differences also, but it's been a remarkable platform. But I wanted to talk then about my history, where I enter the picture, and you never know history. You never know when you're living in history. And I started at AMES, as Tom said, in 1989, and I got there just late, or just a little bit too late I was too late to participate in a mission in the Arctic, looking at Arctic haze. And so we had no airborne programs until '91. We participated in two of them, but they were both unplanned. And the first one was in June of 1991, and we called this the Kuwait oil fire experiment. We flew on we being me and the group that I was working with at NASA Ames, we flew on the University of Washington C-131 aircraft. You can see the engine on the left wing, or right wing on the aircraft in this picture. 700 oil wells were set on fire in January and February of 1991 during the Iraqi retreat from Kuwait, Saddam Hussein's scorched earth policy. Out of control fires. It took almost the rest of the year to put these fires out. These were considered to be some of the hottest fires that ever burned on Earth. They set up tremendous billowing clouds of smoke. This picture here, I know for sure my colleague, one of my flight partners who was at Goddard, NASA Goddard Space Flight Center, Michael King here, I think took this picture. I know he took this picture here. These really good ones here, though, come from the National Geographic photographer, I believe. Right? These were professionals here. But this is what the sun looked like. Very dim. And this we were in Bahrain, 200 kilometers south of the fires, I believe, or even a little more than that. This is a great picture right at the ground. But this is pretty dull, pretty dim. There. This is another picture I think that Michael took, and these things look like stratus clouds, but they're not stratus clouds. It's smoke. It's actually oil droplets that we learned later. And really the origin of those droplets, I don't think that we ever determined whether they were uncombusted oil or whether it was a vapor that had condensed into the droplet phase. But our purpose was to fly through this cloud and try to understand how much solar radiation is being absorbed by these clouds, because one hypothesis went at the time that so much radiation gets absorbed in these clouds, they heat so much, they become buoyant, that they rise, they loft, they become positively buoyant enough that they'll go all the way into the stable stratosphere, which is not easy to do. You've got to be very, very buoyant to do that, but you can do that if you make it really, really hot. If it gets into the stratosphere, it's hard to get it out of the stratosphere. You can circulate this around the globe, and there were hypotheses at the time that this could be maybe a picture of what a nuclear winter would look like, and the nuclear winter scenarios that were published about not even a decade, just a few years before this, had similar mechanisms that get smoke up into the stratosphere. If you change this radiative energy distribution, you can trigger changes in weather and climate. And so this is what we wanted to try to understand: are there possible global consequences of this? If it reaches the stratosphere, the consequences could extend across the globe. We also considered that the smoke was hydrophobic, meaning that it's not wettable. You don't form droplets from these smoke particles. Therefore, you can't rain it out. You can't get rid of it through wet scavenging processes. And so it stays around long, it gets in the stratosphere, and so the consequences were considered potentially pretty significant. This is just an artist's rendering of the types of flights that we flew for there were a lot of other instruments on here, but our interest was trying to find out how much radiation is coming into the top of this smoke cloud, how much is coming in from the bottom. You look at the difference of that as how much is being absorbed, and then you can tell how much it's heating. We determined that at the time that we were measuring, if you extrapolated that over the entire day, it would be 24 Kelvin, or 24 degrees C. It's almost 50 degrees Fahrenheit. A lot of heating. And in fact, this is if you want to think of it as for a real daily average, it'd be maybe 6 degrees C per day, 6 Kelvin per day, which agreed with some of the hypotheses. So we definitely saw a lot of heating. What we didn't see, however, is this cloud ever get much above 4.5 kilometers. It really stayed relatively limited within the vertical extent of the atmosphere. So while we saw the heating, there was other controlling mechanisms, a lot of it being local meteorology, that kept this confined into this narrow range. It never did extend. The consequences for the local region were pretty dire, and they lasted as long as the fire lasted, which was almost the entire year of 1991. But it was limited. We also find out that the particles did have water condense on them, and they did wash out that way as well. So we learned quite a bit from this. Whether there's any connection to nuclear winter is unlikely, but nevertheless we learned quite a bit, and it was kind of a remarkable experiment to get your first experience doing airborne science. So that was so we got back in June. And there was no rest, because what else happened in 1991? Yeah, that happened in 1991. In fact, the first eruption, probably even before we got back from Kuwait. or Bahrain. 3 major eruptions, the real big one here on the 15th. When volcanoes erupt, they do multiple burps and then one big one. It's a long process, and in fact, the whole process started in March of this year, of 1991. But the big one on the 15th of June, look at this. This is 10 trillion kilograms of magma, 10 cubic kilometers gone into the atmosphere. But here's the real important one, because this all comes back pretty quickly, all this stuff. But this 20 billion kilograms of sulfur dioxide. Why is that important? This gets oxidized into sulfuric acid droplets. Again, very, very buoyant. This gets injected into the stratosphere. You form sulfuric acid. It can stay there for years and have large consequences on the climate. Whoop. Not right now. It's injected more particulate into the stratosphere than any eruption since Krakatoa in 1883. Within a few months, sulfuric acid droplets covered the globe. Global temperatures dropped by about 0.5 degree C. Ozone depletion increased. For the related reason to why polar stratospheric clouds enhance ozone depletion, because you have these surfaces upon which this chemistry can act quite efficiently. The surfaces being these little aerosol particles. Our role in here was, well, this is a cartoon kind of depicting what the climate consequences are, ignoring the chemistry here, which I usually do. What this cloud does is block some of the solar radiation reaching the surface, so you get cooling down because of reduced solar radiation at the surface. You get some warming at this altitude because these particles can absorb infrared radiation. Oh, yeah, I have to show this. So Odell Coddington sent this to me yesterday. It's kind of remarkable. This was NASA's image of the day. How we dialed this up so this is from the space station a couple of years ago. But this is one of these great pictures, and you've probably seen this. And there's a lot of these from the shuttle as well. This is from the International Space Station, where you see these edge-on views of the Earth, and you can actually see the layered atmosphere, and it's pretty remarkable. So that total 10 kilometers that we live in is right here, or that the climate occurs in is this thin layer here. Stratosphere above there, but what really makes this remarkable, it doesn't even look real. It looks like a painting. Is the crescent moon there.
Are the colors on that real?
I would yeah. I mean, it's
NASA likes to.
Yeah. I mean, this is just a camera, though. From one of the versus a few band, but it's a good point. Here's a contrast from 1991, a few weeks after the eruption of Pinatubo. This is from Space Shuttle Atlantis, and now you can't really compare this, but well, you could if you didn't have this aerosol cloud. But this is the stratosphere here. This what you're seeing edge on. This dark band up here is the Pinatubo cloud. These are thunderstorms over South America. These are probably close to the tropopause here. So it's probably not too far above these thunderclouds is where the stratosphere begins. And so this stuff is all up in the stratosphere. This happened within a few weeks. And this is what we noted is that, so we did a mission, another very quick response mission. This time we flew down to Barbados. Coincidentally, it happens to be the same latitude as Pinatubo on the other side of the planet, but not a bad choice if you have to go do a mission. There's Pinatubo at 15 degrees north. We flew these transects north and south, trying to see gradients, trying to see changes in the cloud thickness, and using these measurements. And these are measurements of the optical thickness of this cloud, which can tell us how much sunlight's being reflected, and really from that we can determine how much cooling you can get at the surface. We can also use these to determine the sizes of the aerosol particles. And so you can see this pretty sharp gradient, and we had some flights that went into the southern hemisphere, and we noted that the cloud had already crossed in the southern hemisphere. So, came back from that mission in July, and 2 years, all of 2 years into my career, and I'm getting a lot of attention already. These really high-profile missions. The Pinatubo mission was really exciting. We're getting calls from local television, radio stations in the San Francisco Bay Area, and giving them interviews. And of course, they wanted us to tell them that it's going to snow in San Francisco because of the cooling. And this half a degree, while significant, is not too different from normal climate variations. This is the problem with detecting climate trends. We've got to extract those out of the variability that climate does anyway. And it's hard, and it takes time, and it takes a lot of care. So, they don't really like real, I learned a very good lesson very early on that, the media doesn't really like, they don't like scientists who want to be too careful. They want you to be provocative, and the wilder you are, and then they can get two opposing people, and then they can have a hour-long show. But so it so happened that my boss at the time, who was taking most of the media calls, went on holiday. And so who called? He was gone. Who calls but the CBS Evening News? Now, this is before, I think 91 was before CNN, wasn't it? So, the nightly news was the star of the news, was these half-hour news segments. CBS Evening News. Wow, okay. I guess I'll talk to them. They come, they filmed a segment, and we did a few takes, and they told me the day it was going to be on. So this was exciting. We're into August by now. So this was awfully exciting. So I was set to be famous. One small thing. That was the day that I was supposed to be on the CBS Evening News. There was bigger stuff happening in the world at the time. And so this is why you say, what a year 1991 was, right? So, you forget about this stuff now, but at least, there's Yeltsin there. I don't know if you remember these things. That's the Russian, I believe that's the Russian White House. You remember they were actually firing on their, well, that may have come later, but this was the coup. The old guard was tired of Gorbachev and his reforms and tried to put an end to it. What it ended up doing is actually accelerating the whole end of the Soviet Union. But so I ended up on the cutting room floor, and I later talked to the director, and he said, it was going to be okay, but you didn't really tell us enough. He wanted me to be more certain about the climate consequences of Pinatubo 1 month after the eruption. So not quite famous. But we've been busy with science ever since. This is a great timeline that Odell Coddington, who works with me and many others here at LASP, put together when she gave a public lecture here. And I'm guessing it was 2011 because that's when this ends. And these are just, I'm not going to go through these and what all the science objectives were, but there's 17 different experiments listed there. This starts, a little bit earlier than my arrival at CU. I arrived here in 2004, but we extended a lot of the science that we did, continued it coming to CU. A lot of these missions continued the types of science that, when I came to CU. So we want to come up to present time and talk a little bit about what we're doing here now and some of the missions that we've done. And I thought, LASP is big in, LASP started, with sounding rockets. That was our origin, and then we did orbital missions. And that's our bread and butter. But there's some of us refugees from other places who've done airborne science, and there's some people here who are starting to do airborne science, especially in the engineering division, and they've put their great skills and tools to work at doing airborne science. And why not? right? So I just put some of these pictures together. There's some really important people here. Brian Toon, who is another refugee from AMES, he led a lot of these. He's not an instrument builder or measurement maker, but he actually has led a lot of these science missions, and a lot of his science has actually directed a lot of what we do. There's Michael King, who I mentioned. Who's been doing this, doing airborne science even much longer than Brian, who has built instruments at NASA Goddard, continues to be involved in airborne science today. There's Odell. I'll only mention the people that are here. There's Eric in the back and Bruce. Sebastian's not here, but I want to say that a lot of these people, the people that I work with, are probably instrumental in me still doing airborne science, and because they've done such a great job, I think that we can continue a lot of what we did. I probably wouldn't be doing this, which would be a pity because we brought a lot of students, a lot of great students through this program. But then in engineering, we've got a couple people here, Aref and Darren, who come from the airborne science community. We've got Pat, who probably started doing airborne science since here. Brian, Tom Sparn, who are actually leading, managing, or we propose to manage airborne missions. Ginger leads the calibration group, which works with a lot of the instrument builders and new instruments that we're preparing for airborne science. We've adopted Scott Kittleman for LASP for this purpose. Scott is not strictly LASP, but he spends enough time here that we're going to call him LASP. Recent missions, I better go through this quickly. One is called Seekers. I guess you don't pronounce that "for" there, which is good because I don't know how you pronounce it. Study of emissions and atmospheric composition, clouds, and climate coupling by regional surveys. This is one of the missions, recent missions that Brian Toon, who's now here, both at ATOC and at LASP. He was the program scientist for this mission. You can see the DC-8 and the ER-2 here in the foreground. This is lovely Houston in August. No better time to be in Houston than in August. Sounds like people don't know Houston. There was another airborne, or another platform here, a Learjet from this company, this local Boulder company, which measures particles in the atmosphere. I won't go through all, there's the goals. Air chemistry, understanding how gases and aerosols evolve, how they interact with clouds, changing the atmospheric heat budget. That's the role that we play in measuring radiation, and also, again, calibration validation for future satellite measurements. Here's a program that our radiation group has participated in for 3 years now. This is so we've flown on this amazing platform called the Global Hawk. Unmanned. They call this an unmanned aerial system. Sometimes it's an unmanned aerial vehicle, unmanned airborne vehicle. What it isn't is an unpiloted vehicle. If anybody calls something unpiloted, you better duck because it's piloted. This was a mission. It's called Airborne Tropical Tropopause Experiment. Eric Jensen is a colleague who's still at LASP, or still at AMES, NASA AMES, who is the lead for this mission. This was to study the exchange of water vapor and other gases at this boundary between the tropopause and stratosphere in the tropics. It's very important. It's very important for climate regulation. If we can get water into the stratosphere, and so it's very important for climate. And ozone studies also played a very big role in this experiment. There were 3 measurement legs of this experiment. The most recent was in Guam. Bruce Kendall spent almost 2 months in Guam. Did all of how many flights, Bruce? Did you do 3? You did 3?
6 of them.
But were you there for the?
Not
Yeah. It's a temperamental vehicle. It's not simple. There's and the topic of another one of these talks is the future of these types of aircraft. Well, I guess I should show here. So, I mean, look at this. You can keep this up in the air for 30 hours. You ask any atmospheric scientist, would you like to stay up in the air for 30 hours? You'd definitely say yes. The problem is getting it up there to begin with, though, especially, I mean, it's a very sophisticated thing and not simple to fly. Look at this, 11,000 nautical mile duration. Flies 15 to 20 kilometers. This is a little bit of exaggeration, as long as you don't put instruments on it, but it really can't get quite that high. The payload's pretty significant, though, for a UAV. I mean, that's about a little less than half of the ER2 payload, so that's important. We do balloons, and I'm sorry I'm not going to give this a lot of time, unfortunately. Lars Kelnes, who gave his own last public lecture, I think a year ago, does balloons. He measures ozone in that same South Pole vortex that we saw. I do have a movie. This is a real fast one.
The South Pole. On this
Lars
region
told
of
me
the
not
Earth,
to show
there's a
play
natural
the sound, so
phenomenon,
I've got to
the
play the sound.
vortex. It's a vast whirlwind which forms in the stratosphere during winter. Its study enables to understand better the way the global climate of the Earth works, and the measures are then confronted to those of satellites and meteor.
Okay, so that was fast enough that we can play it over. What did we see? All those little dots
Here,
are
the South Pole.
balloons.
On this region of the Earth,
They're
there's a
tracing that
natural
circulation
phenomenon,
into the polar
vortex.
vortex.
It's a vast whirlwind.
Each one
which
of those
forms in the
lasted about
stratosphere
90
during winter.
days,
Its study enables to
at about
understand
70
better
kilometer
the way the
altitude.
global climate of the Earth
Lars
works,
is
and the
our
measures are then
resident balloon
confronted to
expert
those of
here
satellites.
at LASP.
Super pressure balloons?
I don't know if these ones were. I think he's flying other missions on those, but I don't know if these were. Lars is really the expert to talk about balloons. But remember, we said that another important part of airborne science is instrument testing. We have mission concepts, future space missions, to study the Earth's climate like we've never done before by ultra-high accuracy measurements, an order of magnitude better than we've ever done before. And this is a colleague of mine at LASP, Greg Kopp, is the lead scientist in the development of what we call a hyperspectral imager. Really what this means is that we image the Earth, but for every pixel, every one of those pixels in that image, we have lots and lots of wavelengths. That's the hyper part of it. He flew this and tested this on a balloon last September. It actually, the remarkable thing of this instrument, unlike any other past instruments, is that it's going to use the sun to calibrate. And so it tested this calibration during this balloon flight. So there's an image of the sun. This is a ground image here. It also looks at the moon for calibration, to calibrate some of the optics in the instrument. But I'll go past this. What we get is what we call an image cube. There's our image of red, green, blue composite. Every one of these pixels then has a spectrum. So this is wavelength varying down in the vertical direction. Across here is you see variability due to surface variability. So this looks like a river delta here, and that's this big black chasm this way. But in this direction, these are atmospheric absorption bands. These are water vapor, oxygen bands down here. And so we hope to soon be in the business of analyzing lots and lots of data like this to better understand Earth climate. What lies ahead? Lars has a balloon experiment. This is the one. These might be the balloons that you're referring to, but I don't. This is going to be in the tropics, looking at the tropical tropopause layer. Balloons that fly for 3 to 6 months. Over a 2-year period, he's going to fly 40 such balloons. This has been funded. We have a proposed mission. This is one that we're very proud of. It was submitted early this year to study interactions of the Arctic atmosphere, and particularly clouds, with sea ice. It's been hypothesized that clouds play a very, very important role in the sea ice loss. There's been correlations between low cloud amounts and these extreme losses of sea ice. The most recent that we had, we keep setting records. In 2012, we had a sea ice minimum we're losing sea ice at a remarkable rate. It is the place on the planet where climate change is occurring most rapidly. We've got a 4-year mission plan flying 6 weeks in each of the years between 2016 and 2019, flying all sorts of instruments, including that hyperspectral imager that you just saw. This AMES, which has its heritage to an instrument that Michael King developed when he was at Goddard, dropsons to monitor the atmospheric state variables, a LiDAR and a radar. So we're very excited for this mission. Hope it gets funded. But here's something that maybe is a little bit telling, is that there's a Predeclaim mission going on now, and our group was invited, led by Sebastian Schmidt, to participate in this. You could think of as a mini Acclaim. It doesn't have the radars and LiDARs, it doesn't have a hyperspectral imager, but it has some of the radiometers that we're going to fly. And this was just put together very, very quickly by NASA headquarters, and it's going to occur this fall. We're hoping we can read the tea leaves that that they're showing us their hand, and that there's a good likelihood that we'll get the Acclaim mission funded. It has some similar mission goals. I'll just see here: develop a quantitative understanding of the relationship between changes in Arctic ice and regional energy budget as influenced by clouds. Very simple version of Acclaim. Nevertheless, it's exciting. So I'm done. I just wanted to say here that there's a lot of opportunities for students. It's obvious that there's a lot of opportunities for graduate students, and graduate students play a large role in this. But there's a role for undergraduate students also, and we saw that in the video with this thing called Student I'm not good with acronyms. Student Airborne something Research Program. Thank you. SARP. There you go. I could have gone to the slide. 8-week summer program for junior and senior undergraduates. Require hands-on research. Research areas include chemistry, evapotranspiration, biology, ocean biology. There's a lot of other science. I focused on very specific areas that are nearest and dearest to me, of course. I don't have the link here, but it's very easy. You simply go to just Google NASA Airborne Science. I cannot find my. Click on this. By the way, even if you're not a student, this is a pretty cool site to look at. And then you go over here to Student Airborne Research Program, get all the information. Again, this is run out of the University of North Dakota. They've been contracted to operate the NASA DC-8 P3 also. Michael, do you know? Do they do the P3? Anyway, there's information on how to apply. It's too late for this summer, but junior and senior undergraduates, I know the director of this NSERC, Rick Shetter, and it sounds like a remarkable program for you undergraduates. So that's all I wanted to say. Yeah, I've had a lot of fun in airborne science. I'm sure I will continue to have a lot of fun, even as I've expanded my interest into space since I've been here at LASP. Thanks a lot for coming out of the rain. Any questions? Yes.
Comment on the role of growing role of UAVs versus whether the scientists are like in the DC-8 or P3, the advantages and disadvantages of those two platforms.
The advantages are pretty obvious. It's very, very long uninterrupted flights. Those don't help me as much as they might help other scientists, maybe those measuring chemistry and particulates, because most of my instruments measure solar radiation, and so if the sun 30 hours isn't going to do me any good unless I'm at one of the poles during summer. But there's a lot that we can do. So the advantages are obvious. The disadvantages there are related to air traffic and safety hazards to other things. You know, you have very, very restricted flight corridors where you can fly these things. I think that you know, this is part of the problem in flying these. Some require chase planes for safety reasons. So you know, they still require a manned vehicle to follow them. And I think, you know, getting those things straightened out, until we get those things straightened out, you know, I can't imagine that it's going to be the workhorse of what we do. You could imagine, though, and you know, in the future they will be. Maybe when Amazon gets things sorted out, when they're delivering packages, which they claim they're going to do, they're developing the technology now with tiny little UAVs. They'll drop them on your porch, and so maybe we'll rely on the private sector to figure this out. But you know, when the sky's full of those, I don't know how we'd be flying everything else. So, but I think those types of the restrictions on flight are really the greatest obstacle. And you know, I've flown on UAVs now for, I mean, I think my first UAV flight was almost in the mid-90s. It's almost 20 years now. And, you know, I can't say that we're really, I mean, each time we do it, it still seems like a technology demonstration flight. It seems like we're testing the platform more than we're doing science, unfortunately. Yes?
Is there any role for like hitching a ride on commercial airliners or other planes that are just...
It's a great question. I know that other countries have taken advantage of that. I know that Lufthansa, I've had colleagues in Germany. I think that Lufthansa's hosted some. I'm not aware of anything done to any great extent in this country. Eric, have you ever heard of something? You know, I mean, one thing nice about flying on NASA aircraft is that you don't have to get FAA certified, and that's not trivial. It's very, very expensive. And in fact, it's one obstacle when we fly on the NSF the G5, wonderful platform. A lot more difficult to integrate instruments on versus these, you know, the NASA aircraft, which fly more or less, you know, the same standard payloads and much simpler to modify. But so I'm not aware of anything done in any formal way. I know, and you hear it proposed. It comes up all the time, I think, but I don't know. If Eric doesn't know, then
There was a program for doing it on FedEx planes.
is that right? Yeah.
There was a program called GASP, which
I've heard of
went
GASP,
a
yeah.
couple of years. And,
Chemistry.
yeah, it was mostly chemistry.
Yeah.
But it was difficult because the payloads had to go in the cargo area, which at that time was not pressurized or temperature controlled,
Yeah.
and they didn't like putting probes out, things like that. And so they tell the scientists at the last minute when the packages could go on, the science package.
Yeah.
And the
It's hard to plan.
instrumentation had to run totally by itself. So, for instance, the NOx instruments, they have to generate ozone for the measurement, which is a high voltage field, usually with oxygen, so that you maximize the amount of ozone produced. And those are susceptible to causing fires, being a safety hazard. So they really didn't like having instruments on fast planes.
Yeah. So again, great in principle and concept, but not in practice. I don't think it's. Nothing more about 1991.
Since you asked,
Yeah.
how did the amount of sulfur dioxide released by Pinatubo compare to like the annual anthropogenic?
Oh, that's a great question. You know, and I don't know that answer. Does somebody else? Does somebody know that? That's a great question. I would imagine it dwarfs it, but I don't know. I don't know. 10 billion kilograms. So I don't know. Oh, I forgot to. So I'll say something more about 1991. So this guy here, I almost forgot this.
I didn't want to ask that question. I know where it's going.
You know where this is going. We had a couple interesting flights on this Convair 131. One time we were flying over the Persian Gulf, which is the side of the Gulf we were on. It's called the Arabian Gulf, by the way. Not called the Persian Gulf in Saudi Arabia on that side. I think didn't we have a flight where there was some mix-up in communication of the pilots getting the radio frequencies to air traffic control, and so we were not communicating, unbeknownst to us, and we found out later. Well, the pilots told us later. I think we had a Saudi gunboat trained on us for the duration of one of the flights, so we were happy. And that was the flight that you and I were both on. But the other one I was talking about was this guy who went on to be. I don't think he was went on to be the NASA Earth Observing System project scientist, but not yet. There was a hole in the floor of the airplane. It was about this big, right, where they had a LiDAR. I mean, this is one thing. One thing great about aircraft stuff is that, I mean, you put stuff together quickly. If the plane gets up in the air, great, and maybe you can make measurements. So we got a big hole here.
It's unpressurized plane.
Yeah, that hole ensured that we were unpressurized. Yeah, he was dropping apple cores. He'd eat these lunch and apples and dropping apple cores down into the Persian Gulf, and
How did that affect the measurement?
we saw it, and no, we didn't have a LiDAR, so didn't affect the measurements. But anyway, yeah, crazy times. So, anything else? Thanks a lot.
Thank you.